Hi everyone. Today we are going to discuss the Deep Dream algorithm. It's a method that can be used to help understand and visualize what different layers in your convolutional neural network do. With this method, you can also create interesting artworks because it helps you to hallucinate different patterns into an image. The resulting images often look like images from a dream, hence the name of this algorithm is Deep Dream. Here, I'm listing you some interesting reading materials about the Deep Dream algorithm. These are blog spots and sample codes. If you have a chance, please take a look at them. When we use convolutional neural networks for image classification, typically we are given a neural network structure, and we also have a training set of input images with class labels. Using gradient descent, we train the weights of the neural network such that it can achieve a good performance on our training set. Here we do something different. We assume that our neural network is already trained, which means that the weights of the neural network are already fixed. We will not change them in this algorithm. For any given input image, we can calculate the activations of the neurons. Usually, the predicted class label corresponds to that neuron of the very last layer, which has the highest activity for that given input image. Now you can ask the question, how would that image look like that maximizes the activity of a given neuron in this neural net, assuming the neural network itself is already trained, that is, the weights of the neural network are fixed? To answer this question, we fix a neuron. For example, in this example, we fixed the neuron that is on the last layer of the neural network and corresponds to the class label of a banana. Then, starting from a random image, which is just the Gaussian noise as you can see here, using gradient descent, we keep updating the image with the goal of finding that image that maximizes the activation of that selected banana neuron. As you can see here, we dreamed or hallucinated these bananas into the random noise. So instead of tuning the neural network weights, for example, VGG19 or inception neural network weights, here we tune the input image of the network starting from random noise with the goal of maximizing the activation of a selected neuron. As you can see in this case, this random noise image converges to this weirdly looking image showing some bananas. In other words, we dreamed or hallucinated these bananas into the random noise. Here, I'm showing results from the same experiment, except that here we selected different neurons on the last layer of the neural network. So, for example, if you choose that neuron on the last layer that corresponds to the end class label, then we would get this image that maximizes the activation of that end neuron in the last layer. Similarly, if we choose that neuron that corresponds to the starfish class label, then we would get this image. If we choose that neuron that corresponds to the class label parachute, then we would get this image. Instead of choosing one specific neuron on the last layer, we could actually choose any neuron on any layer or any groups of neurons on any layers. And we could ask the question, what is that input image that maximizes the sum of the activations of these selected neurons? For example, in this VGG neural network, we could ask, what is that input image that would maximize the sum of the activations of the neurons in the conv4 and the conv5-3 layers? Depending on which group of neurons we choose, as we will see, we could get very different results. Here is an example what happened when we choose layer mixed 4D with channel 139, and we wanted to maximize the activations of the neurons on that layer starting from a random noise. As you can see, after some iterations with gradient ascent, we can start to see these flower-like patterns in the image. This image is still very noisy. It has many high-frequency components. To make this image visually more appealing, at each update step, we could filter out some of the high-frequency noise components and update mostly the low-frequency components. One of these techniques that can achieve this goal is called Laplacian filtering. Another issue with this image is that, as you can see, there are some big parts of the image where there's not much happening. All hallucinated patterns are on the same scale. To overcome this difficulty, we often zoom into the picture and then repeat the dream dimming process on the scaled up image to make sure that there will be smaller hallucinated details as well in the image when we scale it back to its original size. If we feel like we don't have large patterns in this image, then we could just zoom out from the original image. That is, we could just scale it to a smaller size, and then we can repeat the deep dreaming process in this smaller scale image to get larger hallucinated patterns in the image. These ideas are called deep dreaming on different scales, or multi-scale deep dreaming, or deep dreaming with octave scales. Here you can see what happens if we use the Laplacian filtering and the multi-scale ideas during the deep dreaming process. As you can see on the right-hand side, the resulting image looks less noisy, it has smaller scale hallucinated details as well, and as a result, the image is visually more appealing. Here you can see what happens if we choose a different set of neurons whose activations we want to maximize. Here we chose the same mixed 4D layer that we used in the previous example, but instead of using channel 139, here we used channel 65. As you can see, this image is very different from the previous one. Here is another example using the mixed 3B layer and channel 121. As you can see, again, this image is very different from the previous one. Instead of just using one layer, we of course could use multiple layers. Or instead of just using one channel, we could use multiple channels too. Here you can see how the generated image looked like when we used channel 139, and here you can see how the image looked like when we used channel 65. If instead of using these channels alone, we would try to maximize the sum of the activations on these two channels together, then this would be the resulting image. These hallucinated patterns look like a combination of patterns from these two channels. Instead of starting the deep dreaming method from a noise image, we could also start it from an arbitrary image. In this case, we will hallucinate patterns into this image. Let's see how it works in practice. So this picture was the original image. And here you can see the deep dreamed image when we try to maximize the sum of the activations of the neurons on the mixed 4C layer. If we try to maximize the activations of channel 139 in the mixed 4D layer, then we can see the flower-shaped patterns again. Finally, I'm showing one more result. This was the original image, and we tried to deep dream different animal-shaped like patterns into this image. In what follows, we will look at some Python Jupyter notebooks that show how to implement these algorithms with a few lines of codes. Here, you can see links to the Google Colab notebooks, and I also uploaded these codes to GitHub. We will discuss them now. This code is a very simple demonstration for the deep trim algorithm. Let's quickly connect to a machine with GPU, and that's all we need. We are connecting now. Let's check what kind of GPU we got. So in this case, we will have a Tesla T4 GPU, as you can see here. First, we will import TensorFlow, we will import NumPy, Matplotlib, and some other functions that can help us displaying images. Here's a link to an image that we will use to demonstrate how this code works. Here are just some functions that help us downloading, preprocessing, and displaying an image. The first function just downloads an image from the given URL link, and then it returns the image as a NumPy array. The second function just helps us preprocess an image in such a way that if the original image was in the -11 region, the pixel intensities were in this region, then it transforms them linearly into the 0-255 region. You can see it's just a very simple linear transformation. And then we create a TensorFlow tensor from this image. And the third function just displays the image with the display function. The next line downloads the image and then shows this image. So let's run this cell. And as you can see, we downloaded this image and now we are displaying it. We will use the Inception neural network for this demonstration. If you use Keras, it's very easy just to download pre-trained neural networks that are often used in different demonstrations. So here we just download the Inception neural network. That's done. We call this downloaded neural network base model. Let me display the first 5 layers of this neural network and the last 5 layers. And I'm also showing the shape of each of these layers. As you can see, first we get the input layer, which will get an image. The requirement is that it's a RGB image. These 3 coordinates stand for that RGB image. This is the X size, this is the Y size, and this just indicates that we can work with a batch of images. Then we have a convolutional layer, a batch normalization layer, and here you can see how many channels these layers are creating. On the last layer, which is called mixed 10, it creates a tensor with 2048 channels. We will try to maximize the activations of the neurons on the mixed 3 and mixed 5 layers, but here you could choose whatever you want. So here we select those layers and put them into this list. And as you can see here, we are displaying those layers. Then we create a new network, which is just a subset of the previous network. It gets the same input, the input image as the previous one, but for outputs, we only use the selected 2 layers, the mixed 3 and mixed 5. So we will keep all the layers that are between the input layer and these mixed 3 and mixed 5 layers, but we will not need the rest of the layers from the original Inception neural network. The original Inception neural network had 311 layers. This new one because we just need everything up to the mixed 3 and mixed 5 layers, it will only have 165 layers. As we discussed, what we need to do is that for each image, we will calculate the sum of the activations on these mixed 3 and mixed 5 layers, and we will try to find that image that will maximize the sum of these activations. So we create a loss function for this. The loss function, just for each image, calculates the sum of the activations of the neurons in these mixed 3 and mixed 5 layers. So this loss function gets an image and a model. And here, as you can see, we calculate what's the output of this model. And those will be the activations that we want to maximize. We calculated these activations, and then we add all the activations of the neurons in these layers. For each layer, we calculate the sum of these activations. We create a list from these, and then we add these activations in this list. In other words, we just add all the activations of the neurons in the mixed 3 and mixed 5 layers. So this is our loss function. What we will need to do is that iteratively we want to update an image using gradient ascent such that at each update it will increase this loss function. Just to show how this loss function, so let's define this loss function, and to show how this loss function works, here you can see that the loss function gets an image, in this case the original image, and gets a model. I'm showing how it would work for the base model and for the dream model. And as you can see, it indeed calculates a real number. We want to find that image that will maximize this real number. For this maximization process, we create a new class that we call Deep Dream class. It will get our model as its input, and we can set up the parameters like how many steps we want the gradient descent to do, and what should be the step size, the learning rate in the gradient descent, or gradient ascent in this case. So we set how many steps we want and what should be the step size. And then, as you can see, in this case, we calculate the gradient of the loss function with respect to the image. The image is not a TensorFlow variable, so by default, TensorFlow wouldn't calculate the gradient with respect to it. But if we add with the tape.watch command the image, then we can ask TensorFlow to calculate the gradient with respect to this image. And that's what we do here. We tell TensorFlow that here is this loss function. It will get an image as an input, and the model is its other input. And we will need to calculate the gradient of this loss function with respect to the image. So please watch for that. And then this is the step that actually calculates the gradient of the loss function with respect to the image parameter. After we calculated the gradient, we can normalize the gradient. And then we can update the image that at each iteration, we add a step size parameter times this calculated gradient to the image. We can clip everything back to be between the -1, 1 region. And when we want to display the image, then we can transform this image back to the 0, 255 region. We will run this gradient update steps number of times. So this is the class that we just created. And then let's instantiate this class. So this Deep Dream variable will be an instance of this class. Let's create a noise image. In this case, the size of this image is just 200 times 200, and it's an RGB image. We create this NumPy array, and from this NumPy array, we create a tensor that can be the input of this inception model. For that, we need to preprocess this image that we just created. We do that with this command. And then we can start deep dreaming into this noise image. We will run 5 iterations. At each iteration, we call this gradient descent update. And as you remember, each time we do 10 steps of updates. After we are done, we show the current results with this show command. And because the image that we got is between the -1 region, we need to transform it back to be between the 0 to 155 region. And here we can see each step of the update process. As you can see, we started from a noise, and then at each step, we update little by little. And as you can see, we started to hallucinate these patterns into the noise image. Now let's see the same idea for this original image. We do exactly the same thing, but the image variable will be the original image that we downloaded instead of just using a noisy image. The pixel intensities of this original image are between 0 and 255. We will process this image again, and then we will run 5 iterations of the deep dream algorithm. In each iteration, we will run 10 steps of gradient ascent update. And after each of these 10 updates, we show what the current progress is. As you can see, we started to hallucinate some patterns into this image. This is iteration 0, iteration 1. You can see the loss function is increasing indeed as we wanted. And this doc has more and more of these hallucinated patterns. Alright, so this is how the deep dream algorithm works. There are tons of improvements on this. I left some code for each of these improvements. One of them is that, as we discussed, we could use multi-scale updates. So we could zoom in and zoom out. That is, we could rescale this dog image to smaller and bigger and hallucinate in each scale to these images and then just combine these images. Another issue with this algorithm that currently we cannot create very big images. And the reason for that is that the whole image is loaded into the GPU and we calculate the gradient with respect to all the pixels of this image. This is not scalable. If your image is very big, then you can run out of GPU memory. And to overcome this difficulty, you can split the image to tiles. For example, each tile can have a size of, say, 512 times 512. And then you can do the deep dream algorithm in each of these tiles and then combine the results. Another improvement is that as we mentioned when we discussed the slides, is that you could do Laplace filtering as well on these images. That is because the resulting images from the deep dream algorithm might be too noisy. You could filter out some of these noise, and you can do that with the Laplace filtering algorithm. For each of these, you can see some Jupyter Notebook codes. If you have some time, please take a look at those codes. And if you have any questions, please let me know.